hopefully, at the lower layer, you can throw out a lot of data that's not interesting. And then by the time they get to like very high level module where you have to make a decision, you want to probably apply some sophisticated analysis, and the algorithm would likely have some false alarm. But then maybe hopefully at that point the data stream has been reduced so much that the base rate is high enough, because at each layer you are essentially filtering out data that would not be interesting. You're keeping the data that will be likely contribute to the intrusion that you are analyzing. So by the time they get to a higher layer, the base rate is high enough. The point is that then you're giving a chance for your algorithm to actually work. Okay, so that's the main motivation. So there's some nice properties about the cascade. So for example, we can claim that if you look at a cascade, right, then the Bayesian detection rate of the current module essentially is the base rate of the data to the next higher module. And to see this, you can easily prove this, right? So because you can rewrite the Bayesian, so you can rewrite the Bayesian detection rate as the probability of data is being both produced by IDS as a alert and also intrusion, divided by the probability that this data is also produced by IDS as alert data, right? So the point is that data stream to the next module essentially consists of all the alarms, all the so-called alarm data that are produced by the current module. But within that data stream, only some of those are the real intrusions. So if you think about that way, then it's very obvious that. But this is exactly how you compute the base rate, right? You receive some data, and only some portion of it is actual intrusion. So then you can see that the base rate, the Bayesian detection rate of the current module will essentially the base rate of the next module. So that's claim one. And then this is also obvious. So what we are saying here is that your Bayesian detection rate should be greater than base rate. And if and only if that your detection rate is greater than false positive rate. And you can argue that any reasonable, any allowable IDS would have this property here. Because if you think about it, if you do a random guess, you have like exactly the same, meaning detection rate and false alarm rate would be exactly the same, 0.5. So any reasonable IDS would do better, meaning the detection rate would be greater than the false alarm rate. And we can show that if this is true, then you have this condition, okay? Then you have that property. So just combining these two results, then you can show that the base rate actually would increase from one layer to the next. Just plug in the claim one and lemma one. So that's a nice property. So meaning that in a cascade, you can build out a cascade so that the base rate keeps improving. Now, so that's one aspect of it. But of course, if you have to look at some other metric, right? So the point is that so if it's very obvious that if you assume independent features and algorithms, then the overall false alarm rate will actually would not increase, and same thing for the true positive rate. So this actually is good news, right? Because the false positive rate will not go up. But again, the bad news is that the detection rate would likely to maintain the same or actually go down. So that's the bad news. So when you design a cascade, so some consideration are that you want to filter out the normal as early as possible, right? And then essentially you have to think about how do you break the detection process into phases, where each phase try to filter out some data. And this is normally depends on the knowledge, domain knowledge of the application and the kind of intrusion that you are looking at. And also, you want the module to have very, very high true positive rate, because the overall true positive rate will be the product of all the modules, right? So if you start with something new, something low, then the overall rate will also be low. So essentially you know the point is that you want to specialize the algorithm for each thread. The point here is that so you're asking how will you be able to actually, let's say at the lowest layer of your cascade, how will you be able to come up with a module that has very high very high detection rate about the possible intrusions, and then low enough false positive rate, because I mean, isn't that the same goal that you want to accomplish? Meaning, for the overall IDS, you want it to have high detection rate and low false positive rate. So you say, you know, so how will you be able to actually say that, you know, when you start up, the first module would be able to do all the work or accomplish that particular goal? So think about the argument that you want to filter out normal, right, as early as possible. But how do I know what normal looks like? I mean, that's the problem you want to solve, right? So I mean, isn't that a chicken and egg problem? Yes, in general sense. But if you're looking at a specific kind of anomalies, suppose you say I want to use this architecture style to come up with a system to detect fast scanning worm. So you know certain properties of fast scanning worm. So meaning you actually look at a subspace of the intrusions. So under this kind of constraint, you can actually come up with some algorithm that would actually be able to filter out normal very early. Normal here means that something that you are not interested in. Okay, you can do that. So what I'm advocating here is that it's very difficult to design an anomaly IDS to actually cover the whole attack space. You might as well just divide and conquer. Essentially say, okay, here's subspace, I know the properties, I can build a cascade, specialize it, and have very high detection rate and all that. So here's give you one example. So we use the cascade to actually come up with this system to detect fast scanning worm in your local network, right? So the first phase, essentially, we say, okay, when we want to, so the intuition is that if you look at what are properties of worm, right? So obviously, first of all, the worm has to infect some host, and then it would, after the host being infected, it would go out and then scan some other host. So you can think about this as two stages, right? So that's why at the first stage we look for infection-like activity. Okay, so meaning that you know a host is being hit at one point and then go out and have some outgoing traffic from the same port. And of course that's not enough, right? So then the next phase is that for those hosts, then you look at its scanning activity to see whether it's scanning in an abnormal rate. Okay, and then we say, okay, then if you can identify a host where it has this infection-like behavior, meaning it's being receiving traffic at one port and then sending traffic on the same port, and also its scanning is very scanning rate is very high, then we know it's a victim of the worm. Now, this is not new or not surprising. What's surprising here is how we structure the module. We purposely break this into two phases, where the first phase actually can filter out a lot of data, whereas a lot of IDS just put these two tracks in the same rule and just apply, just analyze all the data. So that's the difference here, and we can argue that this would actually produce more efficient and accurate IDS. So the detail of the algorithm probably is not as important. For example, to actually detect infection-like behavior, it actually is easy, right? You just keep two Bloom filters, and you actually check in the timeline, what are the sort of the hosts being ports are being visited at the previous time window, and then whether the same ports and same hosts are sending out traffic at the same time in the next time period. That's easy. And then for the anomaly scanning detection,